Hi, and welcome to part 2 of this tutorial, in which we're trying to make a render engine inside Blender using geometry nodes. If you haven't watched part 1 already, I recommend you do, link in the description. But if you don't want to, here's a quick recap. We built a camera procedurally that adapts to the focal length with the grid as a sensor that adapts to the render resolution. Then we fired rays toward the sensor, hitting our objects to find out what the camera is looking at. From there we used the recast outputs to calculate some render stuff. And what we did so far is an alpha, mist, normal, position, and UV passes. Today, let's make this camera able to see light and work on a diffuse pass. By the way, what you're watching was rendered in cycles, and what's inside the camera was rendered with this render engine with its result piped into cycles as an attribute, which makes it a dream within a render within a render.
A dream within a dream. 2 levels.
Genuine inspiration, right? Now in a dream, our mind continuously does this. We create and perceive our world simultaneously, and our mind does this so well that we don't even know what's happening. That allows us to get right in the middle of that process. Now this is where I need you.
Sorry, he talks too much. He thinks he can get into your dream and use your subconscious to convince you to subscribe or something. What an idiot. Before I start, I want to thank this user from Blender Artist. After I uploaded the first video, he suggested a name for it, so thanks Suzap, and I'm keeping the name you suggested, Noodle Ray. Because we're playing with rays using noodles after all, even though I made it look like a PCB with my OCD. But anyway, I want to clean this mess and join this node that takes care of those lines inside this one, and have one clean node that takes care of both the camera and the render city. And what's going to change is this geometry output will go to this node and be called extra, and maybe have a toggle for it so we can activate it. The focal length too. The mesh output of the sensor will be called sensor, and the whole group now is camera. Those 3 outputs were meant just to feed this group that we're getting rid of, so they will go away. Let's copy this node group inside this one. Size it what goes to size X. If you remember, this is the aspect ratio from the previous video that we got by dividing resolution X by Y. After that we divided size X by this aspect ratio to get size Y. It goes here. Focal length. Now its output goes as an output. Geometry that we'll be calling extra. Move it to the top. And we have a focal point as an output. Now let's connect our new outputs. Focal point, extra geometry, and yeah, those goes away. Since we are here, let's match our camera with the Blender camera. And the reason why I want to do this is because in this video we'll be comparing our results to cycles. At first glance, you can see that the Blender camera have its origin at the focal point, and we have it at the sensor. So if you change the focal length of the Blender camera, it's the sensor that moves back and forth, not the focal point. So let's change this. Let's dive into this camera group. This is the node that adds the grid, and by default it goes to the origin. And if you look at the blender camera in local coordinates, the sensor is in the negative Z direction. And we want to do the same thing and move our sensor in minus focal length in the Z now. So we'll get a focal length and multiply it by -1 and connect it to the Z component of a vector and use a transform node on the grid and use this vector as our translation. So now we have it. All we need is to update those lines drawing from the origin toward the corner of the sensor in minus focal length in Z2. So this is the node that calculated the previous focal point here that we don't need anymore. They're gonna start from the origin, and for the Z of the second point we'll do the same thing. Multiply by -1 and connect it to the Z. Let's do this for the other 3 lines. Now it's behaving as we want to. Now with the origin at the 0, all these connections are not really needed for the camera. Even if we disconnect them, it keeps working because everything defaults to 0. But I would prefer to keep them because it's easier to read and it keeps the camera independent from the render engine. So if we change this node with a different style of where the focal point is, it will be a plug and play. Let's work on the diffuse now. Finally, I know, right? So how the diffuse shading works. If you look at those objects, let's say this sphere, you can tell that the light is coming from this direction. That's because the surfaces that are facing the lights are brighter, and the more the surface is facing away from the light, it gets darker. You may be wondering why, because this is a diffuse and the light from the same source is hitting this surface and bouncing in all directions, and the same thing here, it bounces in all directions. So if we keep thinking about this as a point that doesn't have any dimension in the real world and the light as one vector, it's hard to grasp. We need to think about it as a surface and the light as a quantity of energy hitting that surface. Allow me to explain. In this illustration, the blue square is the point we're shading on the surface. And this is the light beam hitting that point with a certain quantity of energy. So, please notice I did it the same thickness. When it's coming at 90 degrees, this point is getting 100% of its energy. But when it comes at an angle, you can see that some of it didn't hit that point. So this point was getting less energy to begin with, and reflects from that. And the more the angle, the more the energy lost. And when it's parallel, it gets no energy. So we went from 100% of energy when perpendicular to 0 when parallel. And this is what we're gonna try to do. The diffuse, in fact, is more complicated than that. And there is a lot happening at the surface level, even scattering, but we're keeping the simple model, of course, because there is another important characteristic of light, by the way, which is at any time anyone can stop you and say, oh no, wait, it's more complicated than that. Okay, so we did recast from the camera, sensor, blah blah blah, and now we're here. Let's make it here. Trying to shade this point. The recast gave us the hit position, which is the coordinate of this point, and the hit normal, which is the normal of the surface in that point, that we will be calling A. Now let us assume we have a light here, and we need the vector from that point towards the light, that we will be calling B. Easy like we did before, we just subtract the coordinates of these points from the coordinates of the light. And we are interested to figure out what's the angle in between. And you may have guessed it, the dot product, because the dot product gives us kinda the angle between the two vectors. We will see why kinda in a bit. So obviously we need the hit position and the hit normal. I'm glad I labeled my reroute points here. By the way, don't you wish we have reroute points like this that act like portal? One orange and one blue, and no need for the noodle, and the flow will just teleport. And we need a light, so let's create a new collection for lights. And get the blender point light. And bring this light into our node tree. I really wish this object info node will be more object oriented. What I mean by that is it changes its output based on the selected object. Like in this case, if it's a light, it just gives us the light parameters outputs, so we can use them here. And I think it will give geometry nodes per integration with Blender Core. But now that we don't have that, we make our own. So we need a color and a value for intensity or power like that. Okay, so looking back at our explanation here, the vector A is the hit normal, and the hit position is this coordinate, and the light location is the location of the light. We said we will subtract. So this is vector B. I call it direction to light. And we do the dot product of the two vectors. Let's copy the stored name attribute and let's switch to enable and disable the pass. We will force it to true because we'll be working on this pass for a while. We'll add its toggle in the camera later. So it needs to give us this, and we connect our flow like we did for all the other passes. Let me disable other passes and give our camera a nice resolution, like 50% of full HD. And let's take a look at our dot product result. And here it is. It already feels like we have working light. But if you look carefully, this sphere right now looks brighter than what's close to the light. And that's why I said earlier the dot product gives us kinda the angle. So the exact formula for the dot product of the two vectors will be the magnitude of the length of A multiplied by the magnitude of B multiplied by the cosine of the angle. So the length of the vectors is involved. So the further away the object from the light, the larger its length, and it's gonna give a higher value for the dot product, and the object gets brighter. So we need to take this out of the formula by normalizing the vector, which will give us a vector of the exact same direction but with the magnitude of 1. And of course we don't normalize the normal because the normals are normalized. By the way, are they called normal because they're always normalized, or normalizing a vector is called after them? And here, by disabling and enabling the normalize, we can see there's because multiplying by 1 is neutral and the length is out of the formula. Now it looks more correct. Let's quickly add the intensity and the color. Simple multiplication for both. One as a value and one as a vector. Multiply the intensity and the color. Oops. Now we can see the intensity is working. And the color. Let's go back to white color because I want to show you something. If we use negative for the power light, the light will reverse and start lighting the other side. Since render engines allow negative power for the light, which at first don't make sense until you think about a black hole like an object that sucks light, and it gives a creative freedom, like in your scene if you have a very complex light setup but you want a certain area to be a little bit darker for some reason, you can use negative light for that. This is happening because we're dealing with the cos. If we look at the cos of the angular normalized circle, the cos is the x coordinate while the sine is the y. So at angle of 0 it gives us its maximum value at 1. At 90 degrees it gives us 0, and more than 90 degrees it starts getting negative until it hits -1 at 180 degrees. So the area is not facing the lights or getting negative dot product, and multiplying this by negative power will reverse that. So we just need to clamp our result from 1 to 90 degrees. 0 to 90 degrees, sorry. And we will do this by max node with the value of 0. So if our value is positive, it will be the max. If it's negative, 0 will be the max. Now if we do negative value, you don't see anything because we just have one light. We need other lights to subtract from. And it looks way better with the falloff, which we'll be working on in a bit. Speaking of another light, let's have another light, but before that we will group those to not have a big mess. Now we don't need this anymore. So now let's clone this. And I want to clone the light. It's more fun with two lights. Set this one, point to the second light. And we will mix the result of the contribution of both lights on that same point. And because light is additive by nature, we use add. And here is our second light. Let's work on the light fall off now. In the first video when I showed the diffuse pass, I did mention the fall off distance. And what I did back then was very basic. So I added a fall off distance as a parameter on the light. And like we have a fall off distance. And when I'm shading a point, we just compare the distance from the light to that distance. If it's greater than the fall off distance, I just skip the contribution of that light. If the light is closer and the distance is smaller than the fall off, I just take it, which makes it more of a cutoff than a fall off. So before I start this video, I thought why not try something physically accurate and try to match cycles, and this is what we're going to do today. So now we're gonna use all that shenanigan of matching our camera's behavior to Blender's camera. And we'll use a simple trick by adding copy transform constraint on our camera with the Blender camera as a target. So now it's gonna copy its location and rotation. You can see they're not matching, and that's due to the crop factor of a camera. So if this is confusing, let me know in the comment, or you can Google camera crop factor. There's a lot of nice videos about it. But in a nutshell, if for the same lens you use a smaller sensor, if you just look here, you took half of some of the image like you zoom it, which is equivalent to have a longer focal length. And what we need to do is just between the two cameras to match the ratio between focal length and aspect ratio. So let's try having the same value on the Blender camera and the same value for both here, and we have perfect match. If I do 0.5 half and I do the same thing half, they match. So the Blender camera is doing the right thing because it's just a widget to show you where the camera is. Doesn't want to change its physical size in the world. It adapts the focal length for that. I didn't want to do it for this because we're looking at the render in the sensor, and if I want it larger without changing the focal length, I can. Okay, so let's use same value. We have perfect match. Now we're gonna split the screen. The Blender camera is our sync camera. Press 0 on the numpad. Have it to the right position. Press 0 here too. Oops. the camera to the view on this one. So now if we navigate on this viewport, it's gonna move both cameras. Now we'll be using cycles. So the blender camera is looking straight into our camera, which we can see here. We just need to disable the visibility of our camera for all cycles options. So here we can see through that camera what cycles is doing in our camera here. We can even have a simple comparison with one click. Now to have a fair comparison, since we don't have indirect lighting in, what did we just name already? Nude array. We have to go to cycles and kill all the bounces to 0. For noise, because we have less bounces, I don't think we need a lot of samples. Too noisy. Yeah. And we need to kill the radius for the lights, because in fact even a point light in cycle is a sphere. It have a radius for soft shadow, so any point will sample that same light multiple times. And a spot like this will not reach any of those points, will be darker than a spot like this. We can reach some of it and have some of the energy of the light, and that's what creates the soft shadow. This is something I didn't want to do because I'm leaving with the indirect lighting, and it's a bit complicated in geometry nodes right now because it doesn't handle loops. And that's why I didn't do the area light too, even though I gave it a try by faking the loops using mesh. So instead of a point light, I use a sphere, and then instead of area light, I use a grid, and treat each point of those meshes as a separate light. But it got a bit complicated. For another video, I hope. We can see here it's gray, and that's due to the world shader. But we need to zero out. Zero for the lights. And with 0 radius you can see there is no smooth shadow at all. And we still don't have shadow here, so let's disable it. And we will work on the shadows in a little bit. I prefer to have one light to start with for the falloff. See things from a distance and match the color. We will use drivers to sync between those values. Let's dive into our light group. So if you Google light falloff, seems that everybody agrees on the inverse square rule, which basically says that the light attenuates based on the distance square. So in other words, we just divide our energy by the distance square. So we need the distance from the light. So we can do this. Oops. We can do this and switch it to distance, but I assume it will take the two coordinates and do the subtract that is done here to calculate the vector, and after that calculate the length of that vector. So for optimization's sake, we just calculate the length of the vector. This is rendering, and those stuff can adds up quickly, because if we have a lot of lights and a lot of objects, and maybe in the future multi-sampling, and for each point you sample 2000 times, it starts adding up. That's why I'm trying to optimize as much as I can. And after that we square it. And funny story, when I first ever did this, I grabbed the math node, switched it to power, and because I had in mind to multiply the value by itself, I plugged it like this. So I was doing the distance power the distance, and the result didn't look right. My light was dimming faster than Cycles does, and I kept checking everywhere what's the issue, and the node was close like this, so I didn't see it. I ended up thinking Cycle is not using that rule, so I downloaded Cycle source code, which I'm not familiar with at all. Kept digging. Long story short, it took me a whole night and a morning, I think, and until the day after that I discovered my clumsy mistake here. So, moral of the story, guys, watch your noodles. So it's supposed to be power 2. But again, the power function have a lot of extra tests in it. If the exponent is negative, it's supposed to return the inverse. If the base is 0, don't even bother multiplying, like if you have 0 power 1 million, it will be 0. So when I'm sure I need something as simple as square, I prefer to multiply the value by itself, and that's why I did that mistake. And we will divide the power by this square root, distance square, and multiply, divide, and we already have something that looks like Cycles. Oh, there's another thing. I think we should change the color management from filmic to standard, because filmic will attenuate and have nice highs and don't clip. We don't have filmic here. Now something else about the power in watt. I was trying to find the right value to convert with, but I was impatient. I googled it and I didn't find a quick answer. I was planning to look in the code, which I will do later, but as of now I just had a multiplier and I eyeballed it. Oh, let's put the value at 10 first. So we have 10 watt. And I think something around 0.3 that worked for me, maybe 0.35, kinda. And I think the viewport is darkening a bit, so we switch it to flat, yeah. Looks like 0.2 is about right. Okay, this is the mist number from mystery. Let's have those in a group, like an utility group. This one will be direction to light, distance from light, and the inputs are hit location and hit position. Now let's add another light. Oh, we already did. Now that we added the falloff and have more than one light, let's try the negative power we talked about earlier, and it is working. Let's do the same for cycles. And I think I turned it to white. Yeah, it is working exactly like cycles. Good. Because this I didn't do before, so I did it with you guys. Awesome. Something else that can be fun to do. When I was looking into cycles code, I didn't find what I wanted, but I found the code for the light falloff node. Let me zero this guy. Do we test with one light? So if we add a node for our light and we add light falloff, give us three options for the falloff: quadratic, linear, and constant. Quadratic seems to be the default value already, like nothing is happening. And we have linear and constant. And here is the code which confirmed that. So I assume ray length is the distance, and we have a strand. So if it's quadratic, we'll get the strand as is, and for linear they multiply with the distance. So if we multiply again by t, we will be just canceling the square, which is equivalent to divide by d. And for the constant, it is multiplying by d square, which cancels this completely, which is equivalent to getting this value. So let's do the quadratic first. This is the square. We add another divide. We divide directly by the distance, and that's what we multiply. So if we switch cycles to linear, that's it. So we have quadratic and linear. Constant will be skipping this completely. That's it. I really wish we could add widgets like this in our own nodes as input, like a combo box where you can choose. But since we can't, I'm gonna ditch constant and have the choice between linear and quadratic with just a switch node. So we have a switch for value. And if it's true, we take linear. If it's false, we get quadratic. And we add the input for it. Simple boolean. Name it linear falloff. So now our light will be by default quadratic, and we can switch it to linear with one toggle. Should be equivalent to this and this. You guys thinking what I'm thinking? Like, since you're there and you have the code, why don't we add the smooth quickly? Let's switch this to flat too, so it doesn't darken our render, and keep it at cycles. So this is something I didn't do before, so let me decipher this. So I apologize in advance. And if I fail to do it, I will just cut this part of the video, and you guys will never know. So the strand, which I think, which already passed by this, was multiplied by the square, then divided by the smooth plus the square. So this cancels, so we just add in this one. Okay. And because the linear will be multiplied again by the distance, so it will be, well, because we have an addition, I don't think I can keep this optimization I did here, or I skip it. Yeah, so let's follow the code. I'm gonna add a float. Falloff smooth. And breakdown, we just add it to what we divide to, and we multiply again by the of the linear. This is the square. So this is the square. Need more room. And we add this new smooth, and that's what we divide by to get the quadratic with smooth. So let me have quadratic and give it a certain value for smooth. Let's do 10. So now, oops, if I do 10, yep, working. Cool. And now for the linear, yeah, we multiply again by the distance. So we take the value of strand and multiply it by the distance, I think. Linear fall off with tense mode. Go back to cycles. Tense mode. Linear. Okay. Awesome. This was not expected. Now we have the smooth. 50. 50. Yep. Good. Let's zero this now. Maybe disable the node. Switch this to quadratic. And I think it's time to start the shadow now. Let's activate the shadow for this light in cycles. Like the intro of the first video when I said we do things in reverse, instead of light bouncing in the scene and hitting the camera, we did recast from the camera to just compute what we're looking at. Same thing here, everything in reverse. I mean, look at the camera. The lens is in the back. In real life, the lens is in the front of the sensor, not in the back. Same thing for the shadow. Instead of trying to see if a light shines a light on a surface, from the surface we try to reach to the light. If I can, it means that light is shining light on me. If from a certain spot I try to reach to the light and I can't, I hit an object, it means that object is obstructing the light from me and I am in its shadow. Exactly like you can see it here. The recast node again. And now the target geometry is the objects of our scene when rendering. Because in fact we're not trying to hit the light. We're trying to see to hit any object on our way to the light. So let's make the input for it in the light growth. The source position will be the hit position of the previous recast node, which means the point we are shading right now. We landed there from the previous recast, now we're taking off from there. And the ray direction, it's the vector that have the direction to the light, which we already calculated here. Let's look through our camera. And have this one on cycles, and we take a look at the is-hit Boolean results. We already can see that we have an effect that is matching cycles, shadows. Now let's get a switch node that we're gonna drive with the is-hit Boolean. So when there is a hit through, it's shadow, so we keep it at black. When there is false, we take the diffuse result. And here it is. Let's make our light brighter to see better. If we look again at the is hit, so when we have a hit, it's a Boolean that goes to true, which is 1, it gives a white result. When it's false, it's supposed to be black. But why it's not? So about this noise, which was a nightmare, and I didn't want to make this video long talking about all the steps and pain I went through, but after testing with crazy values and hours in the spreadsheet, I understood what's happening. So we're shading this surface and we're trying to recast from a position on that surface toward the light. But how did we end up here in the first place? the raycast node, the first raycast node brought us here, which means the coordinates we're having are the result of the raycast calculation. Any calculation have a precision limit, which means a margin of error, which translate to those points are not exactly on the surface, so they're shifted a bit. Some on top, some on the bottom. So if we raycast from a point like this, the second raycast will detect this as a hit. And this surface will cast shadow on itself. And the solution is, after I went through a lot of solutions, ironically I found that the best is the simplest, and I saw on DevTalk and or Blender Today video that even Cycle uses this solution to fix similar issues, is from this point we have to move a certain distance, the smallest possible but large enough to exceed that margin of error, and we cast from there. So we need an itty-bitty version of that vector that we add to these coordinates, which will move us here, and that's where we're gonna raycast from. So we know that our direction to light vector is normalized, which means it has a strength of 1. We just need to multiply it by a small value. After that, we add this to the source position to move us here. Now if we plug this as the source position, boom. Now it's clean with nothing in it, like my wallet. And we need to keep this value the smallest possible. But I like this effect. When we start increasing it, the shadows will move away from their objects. That moment when you suck so bad that even your shadow wants to stay away from you. Now let's grab this cube and move it over here. It doesn't make sense, but it's casting shadow too. That's because when we raycast toward the light, we will hit this object even if it's behind the light. So we need to check the distance, the hit distance of the raycast have to be smaller than the distance to light, which means that object is between me and the light, so that's why it's casting shadow. We have distance from light. We add the compare node, hit distance less than the distance from light. And now we just need to combine the two booleans with an AND. So if we have a hit and the distance is less, that's when we have shadow. And the shadow of that cube disappeared. And we have a very nice working shadow. Now let's activate the other light. And activate cast shadow for that light in cycles too. And we are having the same result. And we need to switch this to flat if you want to have the exact same intensity as the cycles. Now let's add a cast shadow toggle like this for our lights. So we'll add boolean And it's as simple as using a switch node. So if that boolean is true, we get the result with the shadow. If not, we just get the previous result with just the diffuse and the falloff. So now we're supposed to, but not working for some reason. Oh, I didn't connect it. Good. This video got too long already, and we still didn't do sunlight. So for the next video, from now on, I will try to make this series in shorter videos. So next time we will do sunlight and try to clean this mess. And after that, we will try specular highlight, because I got a viewer request about it. Meanwhile, here is our render with point lights. I have to say I'm very proud of this. When I first decided to do it, I thought I would end up with some kind of okay render, but matching cycles with a bunch of nodes like this, I didn't see it coming, and that proves the power of geometry nodes. So big thanks to the Blender community and of course the developers for this amazing work. I hope you learned something. Thanks for watching. If you liked the video, give it a like. If you don't like it, feel free to hit that dislike button twice. And after that you hit the like button to tell YouTube that you like it, disliking it twice. And see you in the next video for sunlight. But before I go, here is a cool idea. Why don't we grab a sphere, make it big, let me switch it to wireframe, and we add the geometry nodes on the sphere that will instance the node array camera on every point of those spheres and orient it opposite to the normals, so they will all be looking to the inside, and of course they will be rendering at the same time, and sending the result to this new geometry node that will use that data to do photogrammetry and be able to generate a 3D model of your 3D model.
Are you serious?
You guys take care till next video.